Fine. Now, now today we are basically going to start with the final thing from this chapter, which is called the diffraction grating. Now, in diffraction grating, we have basically a mesh like it's very small in when you in reality it's like very thin and small thing, but we're going to make it like this. So it has many spaces in it like that. Okay, so each of these are called lines, and the number of lines in the whole diffraction grating is called n, like that. Okay, so this part from one line to another, that's basically d. Okay, so basically d is the grating line separation, and n is the number of lines in a unit length. So you can find this d by using the formula 1 upon n, right, like that. So obviously then it will give you the separation between them in the same unit as in the same unit length as n. All right, is that clear? Javeri and Aman?
Yes, sir.
Right.
Yes, sir.
Now, so then in reality, like basically it's sort of thing like this. Okay. So this is the grating, right? And when the light basically goes through, and the light is 90 degrees, right, like that. Then it gives you diffraction, like straight one. In fact, it would be better if I just make it as 1. And then like this, and like that. So this one is n equals to 0, n equals to 1. You just get like you get in laser light, right? So these are like, this is how it gets diffracted. This is the screen and this is the grating. Like that. Now, when you look at it in a 2D diagram from the top, basically what you see is that this is the grating line. Here you see the light. Always, it should be 90 degrees. And then the screen. And then the maximas on either side. It's very similar to what you've been doing previously. Something like that. Okay. So here we have n equals to 0, n equals to 1, 1, 2, and 2. Like that. Okay. Now, what you see right now are the number of orders. Like this is the zeroth order. This is the first order. This is the second order. And same goes for the other side. So it's basically like a palindrome. Like that. Now, here, for each order, there is a separate angle. Like for 0 to 1, it would be theta 1, and from 0 to 2, it will be theta 2, and so on. Okay. So I'm just putting a note here that is very important. You should write that this angle is always measured to any order from the 0th order so this would be d sine theta equals to n lambda. This is the formula that we're going to use for diffraction grating, and that's what you need to remember. D is the same thing that we learned previously, which is basically the diffraction grating line spacing, okay, that we've learned upwards. That's fine. This is basically the angle from 0th to nth order. Depends on what order you're looking at. Of course, this is the number of order. It starts from 0, 1, 2, no matter how many they are. And then this is the wavelength. Wavelength of light. Like that. Alright, so this is just the general formula of what you've been seeing lately. Alright, if you have any questions, please let me know. Okay. All right. Now let's do some questions about it so you guys know what should you expect from this chapter. So the very first question, it says monochromatic light is incident normally, that means it's 90 degrees, on a diffraction grating having 300 lines per centimeter. The angle of separation of 0th order and first order is 10 degrees. Then it says number A, define monochromatic light. All right. And then B, calculate the wavelength of wave, like that. Okay. Now, what you should understand is that monochromatic wave, mono means single, chroma means color, okay, of light. So monochromatic basically means light having a single frequency or wavelength. That would define it, its color and everything. That's why. All right, should remember that. Now, whenever you're going to do any question in waves, okay, it is my advice to you that you always first look at what is expected of you, like what have they given to you. What I mean by that is that in this question there are two keywords. First of all, it's a question about diffraction grating. The next thing is that there are 300 lines per centimeter. So the moment you see this, now you should remember only one formula, and that is for diffraction grating, it is d sine theta equals to n lambda. Always do that. There will be no other formula they're going to use. So you should remember that, oh, it's a diffraction grating question, I should look at it like that. Okay. Now, when you're looking at it, basically, now what you need is, you need lambda. We don't have d, we have n, and we have first order, 0 to first, right? So to find d, we know that n is given as 300 lines per centimeter, n is 1, and theta is 10 degrees. That's the data we have. So first of all, we're going to find d. So d is equal to 1 upon n. So I'm going to just divide it by 300. Whatever I'm going to get the answer in centimeters, because that was in centimeters. So 3.33 times 10 raised to minus 4 centimeters. I'm going to change this into meters. Now let's put it in. So it is 3.33 times 10 raised to power minus 6 sine of 10, and n is 1, and we want to find the lambda. So lambda is going to be 5.8 times 10 raised to power minus 7 meters, which is basically 580 nanometers. Alright, is that clear, everybody? Aman in the video? Any questions you have? Okay. That's pretty cool. You guys have no questions? Alright, give me a second. You can copy this, and if you have a question, you can ask me then. Okay. Okay, now going to the next one. So then in this question, and they say they have given a diagram on diffraction grating, and they say calculate the number of lines per meter on the diffraction grating, as you can see. So the first thing I'm going to see is that it's basically about diffraction grating, which means that I'm gonna focus on only one formula, which is basically d sine theta equals to n lambda. Now I'll see what do I have. I need to find n, which I don't have. For n, I need to find d. I don't have theta right now, but I have the wavelength 632 Newton meter. Theta is not given. And n, because it's next right, so n is equal to 1. I don't know what that is. So to find this, I just need to use some trigonometry, because this is 165 centimeters and this is 90 degrees, and if I want to find this line, this is going to be 76 divided by 2, which is basically equal to 38 centimeters from here till here. Okay, now so this is the 0th order, which means this is the first one, this is the first one. So first of all, let's use a little bit of trigonometry. Now, so you can use tan theta equals to perpendicular, which is 38, divided by the base, which is 165. So the theta should come out as 13 degrees on your calculator. Always make sure your calculator is in degree mode and not the radian mode. Then what you're going to do is you're going to use the formula. You say d sine of 13, this is 1 times lambda is 632, 10 raised to power minus 9, because nano is minus 9. From here, you should expect d to be 2.81 times 10 raised to minus 6 meters. And then you can find n by doing 1 upon d. Because it's in meters, they also need in meters, so that's cool. So then you just need to divide this, and this should come out as 3.6 times 10 raised to power 5 lines per meter, and that's your answer. Is that clear, both of you? All right. Any questions, anybody? Please let me know. Now, the next thing you're going to do is you're going to write a note here. And the note is that for d sine theta equals to n lambda, it is only valid if the light incident on diffraction grating is 90 degrees to the grating. Alright, so it should always be perpendicular, just remember that. Now there are certain cases that we're going to discuss now, and hopefully try to discuss one case at least and finish the whole thing by tomorrow. So first thing is the multiple. Oh my god. Multiple lights incident on a diffraction grating. So sometimes what happens is that not just one color but different colors basically are incident. So let's suppose there is orange and blue color. Naturally, when you see it on a screen, what you're going to notice is that the orange color, which has a longer wavelength, will diffract more than the blue color, which has a shorter wavelength. So initially on the 0th order, both lights overlap, so you don't see any difference here. They will be mixed. So, and then as you go up, right, so the blue color basically keeps on diffracting less than the orange. So suppose this is the 0th order, and this is in fact I'll just write it for the so the orange being longer wavelength will diffract more, and there will be a point where they might even overlap, right? So after many wavelengths, after many time, they will overlap again like that. Okay, so suppose this is the first order. As you can see, the orange has diffracted more, and after like many nth order, at some nth order, they're gonna mix up together. Okay, so suppose in this case it's like the lambda, the orange and blue basically overlap. Like orange has the 4th order when the blue has 5th order, because blue diffracts less, so it means there will be more orders on blue, so they overlap, right, like that. So what you need to remember is that greater the wavelength, greater the diffraction. All right, number one. Then you should remember that both diffract at different angles. I need to highlight this, please. And but at some point they may overlap with different orders, like you see right now that the orange and blue overlaps on 4th and 5th, right? Now, in an overlapping question, it will be a very straightforward question. So you should always remember, like I'm going to write this and then, So it says orange light of wavelength 600 nanometer in 4th order diffraction coincides with blue light in the 5th order. Says calculate the wavelength of blue. All right, so in this one the keyword is this one, coincides. Okay, so you see this, and now you should remember one formula. Okay, I'm just writing here that in case of overlapping of different wavelengths, the angle theta, right, is same for both. That's true. Which means that basically this portion d sine theta, so for the first one it will be n1 lambda 1, and the other one n2 lambda 2. Both are coming from the same greeting, so the number of lines, the slit separation is the same and the theta is same. So now you only going to use this general formula, n1 lambda 1 equals to n2 lambda 2. You should always remember this. For the case of overlapping, this is your go-to formula. Now, this is the general formula for overlapping of waves passing through a grating. Now it is pretty simple because the first wave had the wavelength at 600 and the number of order was 4th, right? The other one has the 5th and lambda was 2, so easily you can find the lambda as 480 nanometer, and that's the answer to this question. Do you guys understand this? Amen, Javeria, any questions now?
No.
Okay, please write this down then. So from this point, we're going to continue tomorrow.